Well, no discussion of the mean value theorem is going to be complete unless we can actually present a proof that the theorem is actually correct. Now, we may look at these graphs and say to ourselves, oh, yeah, well, it looks right. But of course, no good mathematician is ever going to let something like this pass without saying, well, is it always true? How do we prove it's always true? So we're going to say the following. Let's take our mean value theorem again. It says if f is continuous on a closed interval from a to b and differentiable on an open interval between a and b, then there will exist some number c in between a and b such that f prime of c is equal to f of b minus f of a over b minus a. That is the slope of the line secant. So let's take a couple of cases right here. Let's say that f of x passes through the points a f of a, which is down here in the corner, and b f of b. And let line L1 be the secant line through these points. What can we say about the equation of that line L1? Well, L1, of course, has a slope equal to f of b minus f of a divided by b minus a, just like the formula for the mean value theorem says right here. So we're already part way there. So what could we do? Well, we could build the equation of a line. We can build the equation of line 1. What is the equation of line 1? Well, remember, an equation is always formed by taking uh, we could use the point slope formula, right? Our point slope formula is the kind of formula, recall, that goes like this: y minus y1 is equal to the slope m times x minus x1. So we need a point and we need a slope right here. Well, we've got our slope right here. This is m for line 1. Point, well, we've got 2 points. We've got a f of a and b f of b. But let's go ahead. Let's stick with this point right down here, a f of a. So what does my equation look like? Well, y minus the y value at that point, well, that's f of a, is equal to the slope, and my slope right here is the value f of b minus f of a divided by b minus a. That's my slope, that whole thing, times x minus the value of x at that point. Well, that's x minus a. And when we look at that self boys, see, that seems like a lot of work, but that's all right. Bear with me for a minute, right? You understand that we are still talking about this form of the equation of a line. Let's form a second function. This time, we're going to make a function g of x. And what does g of x look like? Well, g of x is basically going to be the function formed by taking the value of f of x minus the y value from our line here, minus this y value. So if you see, what we're doing is we're building a function that basically is always the difference between the y value on this curve of f of x and the y value on this line. All right? So what does that look like? Well, that is the function f of x minus, well, let's see, what is the y value right here? If I solve for y is equal to f of a plus m, which is f of b minus f of a, yeah, minus f of a, divided by b minus a times the quantity x minus a. All right, so f of x minus f of a, minus the quantity here, f of a, plus this quantity right here, f of b, minus f of a, which gives us this function. So now we've got this weird looking function g of x, which has all of these terms to it. But remember, f of x, whatever f of x is, and this entire function right here would form a single value. So what are the properties of this function g of x? Well, for one thing, I know that at x equals a and at x equals b, g of x will equal 0. How's that? Well, g of a is equal to f of a minus, distributing my negative sign here, minus f of a minus f of b minus f of a over b minus a times, well, if it's g of a, it's a minus a. Well, that's 0, right? This is 0. This is 0, so g of a is equal to 0. And we could say the same thing about g of b right here, which I'll just write really. For those of you keeping track right here, when we subtract b minus a right here, we just replaced x with b, right? B minus a cancels with b minus a, so we've got f of b minus f of a minus the quantity f of b minus f of a. Once again, we get 0. So g of x is in fact the kind of function that fits the Rolle's theorem. And remember that Rolle's theorem says that then there must be a place in between a and b such that g of c is equal to 0. Now, how is that important? Well, if we look at the derivative of g of x, g prime of x is going to be the derivative of this guy right here that I've just highlighted, right? We're actually going to be taking the derivative of that. So g prime of x, what is it? Well, it's f prime of x minus, let's see, the quantity f of b minus f of a divided by b minus a times the derivative of x minus a, which is just 1. Right? We asked as that. Remember, f of b and f of a over b minus a, that's a fixed value. This is a constant. We're taking a constant times the quantity x minus a. Take a moment and check that out for yourself. If you take the derivative of constant times x minus a, you're just going to get the constant times 1. All right? And if we were to find a value of g prime of c, we say that would be f prime of c minus this quantity f of b minus f of a divided by b minus a. But remember, we said that Rolle's theorem implied that we have a point that makes g prime of c equal to 0, so 0 is equal to all of this above. And therefore, if we were to set one equal to the other, just add f prime of c to both sides, we would find that f prime of c is indeed equal to f of b minus f of a all over b minus a. Again, provided that f prime of x exists, that means the limit exists, and that the function is differentiable and continuous over the interval. If those conditions are met, our mean value theorem is true.